Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone, good morning, and we're very happy to have Alexander back here, and he will tell us about randomized broadcast.
Thank you, Val. It's nice to see so many familiar faces here. The talk will be slightly different than what I wrote in the abstract. So I decided to do an ambitious talk. So this talk will have 2 acts, but no intermission between them. Okay. So the first act, I'll talk about random broadcast, a paper that I present in SODA with an algorithmic conference like a month ago. And the second act, I'll talk about mobile geometric graphs, a model for moving nodes. And this, I'll talk about like some small extensions I have been doing on this model since I worked on it here last summer. And I'll especially focus on this part on some open problems, very ambitious, speculative open problems. And I reserve more concrete open problems for offline talks. So let's start with the random broadcast. So the setup is very simple. So I have a graph. I have a graph. And there exists a node of the graph that contains a piece of information, say this one. And he wants to spread the information throughout the nodes of the graph. And we are going to analyze this algorithm called the push algorithm. So it occurs in discrete time steps. And at each time steps, this node, the node that contains the information, picks a neighbor uniformly at random and informs that neighbor. It pushes the information to that neighbor. That's why the name comes from. And then you just iterate this procedure. So the 2 nodes will pick neighbors uniformly at random and independently, and we inform them and continue this. But all these choices are done independently, independent of one another and independent of the past. So we can end up picking the same neighbor as in previous steps. So just continue doing this procedure until all nodes have received the message. And this model has been analyzed for a long time in theory and have been suggested for applications like replicated database, where you have a database in many different computers and you have to guarantee integrity of data when there is some update. And also in distributed computing, like achieving consensus in a network or simply broadcast on networks. And if you look at it through a different perspective, you realize that it's just like a first passage percolation problem, right? So each node is choosing edge, and you can just take each edge, the oriented edge from here to here, and you label it with the time at which this node picks this edge. And then it just becomes a first passage percolation problem. And the question of broadcast is just the first time at which all nodes percolate in the sense of first passage percolation.
Right. But it's slightly dependent.
It's like, no. You pick the edge oriented, right?
Each time
it's like oriented.
You get one outgoing edge from every vertex.
Yes, well, because you're taking times like exponential times in each. Yeah. That. But it's still, if you Poissonize this problem, say instead of picking vertex, instead of each vertex picked an edge, you just pick edges with some rate, normalizing it, you can couple them and get the same result. Yeah. That's actually how we analyze this process. So, and we called RG as the runtime of this process. It is the time at which all nodes receive the information. You want to get bounds on RG that with probability going to 1 as the size of the graph goes to infinity. So first, let me start with very simple lower bounds. First lower bound is the diameter. I think no one doubts that the diameter is a lower bound, right? And the second lower bound is log n. And the reason log n is a lower bound is that each node informs at the most 1 neighbor at each step. This means that at each step, at the size of the informed set, at most doubles. So since at most doubles at each step, you require log n steps to inform n nodes. It's very simple. It was first analyzed by Fries and Grimet for complete graphs in '85, and their analysis was later refined by Pittel, and they gave precise asymptotics for the runtime for complete graphs. It's log n plus natural log of n. It's it's very precise. And then there have been 3 years later, Feig, Peleg, Raghavan, and Upfel analyzed this for different types of graph, like hypercubes and random Erdős-Rényi graphs. They gave log n upper bounds that are tight according to these lower bounds here. And especially they analyzed this for general graphs. They show that
When you say random graphs, what do you mean? In what range?
P must be sufficiently large so that there exists a giant component, but not only the critical.
Is there any difference between that and the peak? Essentially nothing.
No. Actually, later.
If you bring it down, then of course there's a huge difference.
Yes. But later, Fontoullakis, Huber, and Panagiotou actually showed that for Erdős-Rényi random graphs sufficiently large, you get exactly the same asymptotic. That answers the question. And then, for any graph, we have the general lower bound of n log n, and this lower bound is achieved by the star graph, this graph, right? The upper bound, yes. So, and it's easy to see because if we start the message in the central node, then it's just a coupon collector problem. It's just a time at which that node chooses all the neighbors. So it takes n log n time. And there's another upper bound that's the maximum degree, delta, times the diameter of the graph, plus some log n, if the diameter is too small. And this is simple to see as well, because if you pick 2 nodes, take the shortest path between them, and then you just compute the time at which this message goes through this path. It's just a sum of geometric random variables, right? And the mean is at most delta, at most the maximum degree. Then, as long as it is large enough, then it's concentrated and you get the results for the upper bound. Now, the paper that's most relevant to our result is a paper of Mosk, Aoyama, and Shaw from 2006, that they studied this for expanders. So they proved that for any graph, for any almost regular graph, where almost regular means the maximum and the minimum degrees differ by a constant factor, they show that the upper bound is 1 over the conductance, which I will define soon, times log n. General. So this means that for generic, almost regular graphs, when they are expanders, they have like constant conductance, then this bound is tight. So let me just quickly review what conductance is. If you take a graph and you take a set of the graph, the conductance of the graph is just a number of edges crossing the boundary of the set. The conductance of the set is the number of edges crossing the boundary of the set over the sum of the degrees of the nodes in the set. So it's the edge crossing the boundaries over the endpoints of edge that touch nodes inside this set. Right? And the conductance of the graph is just the minimum over all sets with at most half of the nodes of the conductance of the set. So it's a set with minimum conductance. And in this talk, I'm going to look at a different notion of expansion, which is vertex expansion. And vertex expansion is very similar. It's just you take a set, and instead of counting edges, you count vertices. So you just count the number of neighbors of the set and divide that by the number of nodes in the set. So this is always a quantity between 0 and 1, and it measures how the sets grow in terms of vertices instead of edges.
Not between 0 and 1.
It is, because if you take a set with half of the nodes, that's 1. And you can only get its minima. The vertex expansion of the set, the graph, is just the minimum.
For a set, it could.
So for some sets, for the graph, it's between minimum and 1. Sorry. For the whole graph, it's between 0 and 1, but for a set, it can be much larger than 1. Yeah. Thanks. And for regular graphs, we can easily relate that the vertex expansion is larger than the edge expansion, and at most d times the larger than the conductance, and at most d times the conductance. Right? Very easy to see. So in this talk, I'm going to look at regular graphs, and for the case where d is not constant. So the general question is there any difference between vertex expanders and conductance or edge expanders, natural expanders in this sense, for large D and regular graphs? So these two quantities look similar, and we prove that the runtime of the push algorithm for regular graphs with vertex expansion alpha is some expression that's similar to this expression for the conductance. It's 1 over the measure of expansion, 1 over alpha, times log to the 5 of n. That's an upper bound. But we get this evil 5 here. It's kind of embarrassing, but it's there. And before I address the 5, let me just say that this result cannot be extended to non-regular graphs. Right? If it's non-regular, then all sorts of bad things can happen. And one of the examples is this one. You have a click, a complete graph, and you add an edge and a vertex at the end. And once this graph itself is a vertex expander. It has constant vertex expansion. And when this node receives the message, it will take him time of order n to choose this edge to inform this node, just because it has order n vertices in the click. Right? So it means that even for vertex expander, you get linear time for the runtime of the push algorithm, while our theorem predicts for regular graphs, this should be like log to the 5, at most log to the 5. But let's address the 5. The 5 there, so can we reduce the log 5? Probably yes. We're not very careful in, we had no real goal in actually getting log to the 4 or to the 3. But one fundamental question is, can you get all the way down to log n and get a result that's almost the same as the result for the conductance? And the answer for that is no. So we construct a graph that's regular graph. Not only regular, the graph is actually vertex transitive. And it has constant vertex expansion. And the runtime of the push on this graph is log square, at least. So I'm not going to show you, it would take me like 5 minutes just to show you what the graph is. But it's based on Ramanujan graphs, just an expander with a Cartesian product of another graph. So for the remaining of this part of the talk, I want to give you some ideas on how to prove the upper bound, which is not hard to prove. I'll give you, I think the proof goes like, when you look things in the right perspective, then you just follow your nose and you get the proof. It's essentially.
But then, can 5 be replaced by 2?
Yeah, the problem is that when you follow your nose, you are in trouble.
But, sorry,
when you follow your nose in the analysis, then that's where you lose all these log factors. We don't know if this is tight.
Do you know whether it's tight or not?
No, we don't know if it's tight. There's still this gap.
Would you have a guess?
We have a brave guess. So, by the way, this is a joint work with Thomas Zauerwald, that's now in Max Planck Institute, and Zauerwald. And we have a guess that it should look like 1 over alpha times log n times log d. In our example, d is n, so we get this log square. In our counterexample here. But that's a brave guess, in my opinion. So let me tell you some ideas on the proof. So the basic strategy is simple. You just look at some time. There will be a set of informed nodes that I call y sub t at time t. And you just wait from that time until this set gets twice as large. Then you compute how much time you need to wait. And after that, you just iterate this procedure log n times. Right? So in our proof, we show that the time you wait is 1 over alpha log 4, and you get this extra log to get the log 3. But the problem is, computing this time actually is, we use different strategies depending on the size of the set of the informed nodes. So we have 3 stages. I will go very smoothly through the stages in the talk. You may not even feel it. But in the paper, especially the 3rd stage, you cannot avoid it. It becomes huge. And that's where the log 5th enters in the game. By the way, it's not going to be even clear in the talk why the fifth. It's just because we lose logs as we go through the analysis. So let's start with the first stage, is when the set of informed nodes is very small. So what happens? The set of informed nodes is very small, let's say this size, and we have a few nodes inside, but each node has degree D. And very small, I mean smaller than D, say D over 2, or even smaller. So there are a few nodes inside, and each node has degree D. So even if there is a click in the set of informed nodes, there is still sufficiently many edges going out of the set. Right? And you can just use this idea to get that initially the set of informed nodes will increase exponentially fast. Right? So in some sense, there is a local expansion for small sets, just because the graph is regular. Right? So you get that after log D steps, you get a set of order D of informed nodes. So we're going to use this idea quite many times.
Which graph is about the worst?
Sorry?
Which graph is about worst?
In which sense?
That way, much of the time you need much less.
No, we can at most grow by half.
Yeah, just the 10 can be improved. Yeah.
Yeah. The 10 is not very important. Actually, we need also upper bounds. We use upper and lower bounds, so that's why we need the constant to be 1. But that's so that notion is going to be very useful because it allows us to define, with this funny name, a friend of a set. So if you have a set X, you have a node S. This node with constant probability to do this local dissemination, this local expansion that I was talking about, so it does like this. If this local dissemination goes inside the set, actually half of it goes inside the set, we call S a friend of X. This notion is actually deterministic. I'm saying that with some constant probability, this node will reach half of its dissemination, local dissemination will reach the set X. It's a deterministic quantity, deterministic definition. And the nice thing is that if S is not a friend of X, and X is an enemy of X in some sense, then S is a friend of the complement, just by definition. Right? Because I'm talking about half, so half must be either in X or in the complement. So either it's a friend of the set or friend of the others. Not all the others, but some of the others. And that's the idea. So so initially we grow this, there is this local expansion, we grow the size of the informed set pretty quickly, but when the size of the informed set gets larger, you cannot apply this idea more, right? Because now we have too many nodes, so we can actually consume all the edges inside the set. So then you have to start looking at the neighbors.
Isn't the spreading at least as fast as in the infinite D over 2 regular graph? And then it's instant.
But
From what you have.
D over 2 regular graphs are expanders. Oh, infinite.
3, not graph, I'm so sorry. I mean the beta lattice. That is surely a lower bound for what you want there. No? Not here. I mean, sorry,
in the beginning, you mean in the beginning?
in the first stage. In the first stage. So you say that is done. You have to do nothing.
But then the size gets too large. The size gets too large.
No, just for the first level.
Yeah.
I mean,
Yeah.
all I would say is that the spreading is at least as fast as the beta lattice is regular in delta over 2.
So now, let's look at the informed set and look at the neighbors of the informed set. And look at one particular neighbor, V. And assume V is a friend of the informed set. So it means if it does this local dissemination, it would send the message inside the informed set. But then you have to choose that, again, the fact that the graph is regular. So it means any path from V to a neighbor here can be reversed and occurs with the same probability. Right? So the probability that there is a path for a given path, the probability that V informs this node from using this path is the same as the probability that the node informs V. And then since V is a friend, there are many nodes inside the set, and V will get informed with constant probability. Then it means that constant fraction of the neighbors will get informed. And since this set's still not, it's larger, but not sufficiently large, too large, just this fraction of neighbors get informed is sufficient for the analysis. It's actually sufficient even if the set is too large, because the nodes are growing by at least alpha, some constant times alpha, times the size of the set. The problem comes when, for example, there is no friend. The informed set is a sad set, so there is no friend of it. So it may take a long time for a given node. You look at a node, it may take time d for this node to get the message, right? Because this may be the only edge that links it to the set informed nodes. Then what happens? Okay, you wait until the first neighbor gets infected, to get the message. But then when this guy gets the message, then he's a friend of the complement. So it means once it gets the message, it informs many people after just a few more steps. Right? And that's the basic idea. That's the two interplays in the analysis. You either have many friends and you just spread the message quickly, or you wait some time to have to cross a kind of bottleneck, but once you cross it, you spread the message quickly after that. So that's the main idea, and then there is a take-home message. Every proof should have a take-home message, right? This is the one of those proofs. So the take-home message is, if you want to spread some information, don't tell your friends. Tell your enemies, right? Because your friends, they'll get anyway, but your enemies will spread it out. Right? That's the take-home message. The problem starts to come when the size of the set is too large. Because when the size of the informed set becomes very large, then look at only one neighbor is not enough. Right? Because this neighbor will, in fact, inform many people. But this many people is still not as large as the informed set. So the informed set is not going to grow by a substantial amount. In this case, this is not important. In this case, what you have to do is you wait some more time until, like, say, half of the friends, the neighbors, get the message. And when this happens, you look at this local dissemination from all of them. Right? All of them will do the local dissemination. The problem is that this local dissemination may collide. And that's where you lose all the logs. When this local dissemination collides, for example, look at V. And V is one of the nodes that receives the message through more than one dissemination. Then not only you have to count how many times it receives the message, but after, let me put this in a different way. First, you consider these disseminations, these local disseminations, as being independent. Right? Think of them as just doing them independently. What happens when V receives, after receiving the message, say, from this guy first, then receives the message from this guy? When he receives the message from this node here, it will start choosing 2 edges per step. Right? Because it's received, since I'm considering the 2 disseminations independently, it will start choosing edges to send the dissemination according to this dissemination, and the same according to this. So we have the problem when you analyze them independently. Not only you have to count how many of these propagations the node is, but also there is a problem that there is conflict. They are making too many choices. So the way we go around this, first we analyze them independently, count how many of these pieces a node can be. We bound this uniformly over all nodes. And then we do a coupling between the independent analysis and the analysis where V is not allowed to make more than one choice of neighbor per step. And then we lose more logs doing this, and we get the log to the 5th. So just one quick remark before, that's the last slide of the proof, of the sketch of the proof. After doing all these calculations, it just follows, when I say follow your nodes, because it just follows by standard principles. You just start using turn-off bound all over and union bound. And that's where maybe we lose some log factors, but still, even if we were to do the analysis very, very carefully, if we're able to do the analysis very, very carefully, we would not get, like, probably being log to the 3. Not better than that. But that's all I want to say about the proof. That before I go to the second act of the talk, let me just quickly say that there is a straightforward corollary from our results to cover time. Actually, there are straightforward corollary from our results to many things, to random subgraphs and other things. But let me mention the one for cover time. The main idea here is that since this process is only picking edges, it's very similar to many other processes, right? It's very similar to percolation, for example. It has relations to other types of process. And here, for example, Chandra et al. In his paper, where he related the cover time with the effective resistance of a graph, he also showed that for any graph with vertex expansion alpha, the cover time is bounded, it's upper bounded by 1 over alpha squared times n log n. And then he said, wait, why square? It was even more embarrassing to see a square there than the 5 in the log. And he asked whether the quadratic dependence on the vertex expand was necessary or not. And it actually follows directly from our result, and we're using a not even tight relation between the cover time and the performance of the push algorithm done by Elzessa and Salvald, that for any regular graph, G, vertex expansion alpha, you have 1 over alpha times some weird log factor, n times log factor of 6. So even though there is an extra log here, which is yet to be bit, we know that the dependence on alpha is linear, is inversely linear, something like this.
But you don't know if you can take the common minimum of these two bounds.
Oh, no. That's yet to be done. So one very speculative and ambitious question is to know if there is any fundamental relation between the performance of the push algorithm and other models like the cover time or random subgraph generation and so on. But that's all I want to say for this part of the talk. Is there any question for this part? Nope? Okay. So let's move on without any intermission. In the second part of the talk, I want to talk about mobile geometric graphs. Let me right away define them. So many of you have already seen me talking about mobile graphs. So I have seen these pictures. So we take a Poisson point we're going to construct a random graph, take a Poisson point process with intensity lambda over the whole plane. That will be the nodes of the graph. And then between any pair of nodes that are within distance r, you put an edge. And the way I'm going to draw the edge is that I'm going to put these red balls of radius r over 2 centered at each node. So nodes will be adjacent when the balls intersect, like in this case. And they will not be adjacent when the balls do not intersect. So that's the starting point. It's a very well-known model called random geometric graphs, or the Boolean model, and also by other names.
One always gives credit to Erdős and Rényi for them. I mean, just you mentioned earlier. And one almost never mentions Gilbert.
Yes.
So like...
Just first defined by
no,
Gilbert.
Gilbert. And then for decades, nothing happened.
Yeah. He mentioned back in the 60s.
Yes, same, exactly the same. In fact, a little bit before Erdős.
Yeah. And then we took this model at time 0, and from that time on, we let the nodes move in space according to independent Brownian motions. So the picture you need to have in your mind is these red balls moving around as independent Brownian motion, and whenever two balls intersect, while they are intersecting, the two nodes are adjacent in the graph. So have a graph for each time in continuous time. Oh, I do have. I didn't prepare to show it, but I do have simulation. And some cute facts is, first, it's stationary. So it means that the Brownian motion is a measure-preserving transformation of the Poisson point process. Or in other words, if you stop the process at any time t, the distribution is the same as the one in time 0. But of course, there are dependencies. And thankfully, there are dependencies, because this allows us to write papers about it. But if there were no dependence, that would be too simple. And then one thing that we know is that there exists a critical intensity lambda c, such that, and it was proved by Vandenberg, Mister, and White in 1997, that at all times, it happens that if it's a case that lambda is smaller than lambda c, then at all times, all connected components are finite. So there are no exceptional times. And this is the picture I'm showing here. If I show you the largest component in the box, it will be this green component here, which is much smaller, relatively smaller than the box I'm showing. But if lambda is larger than lambda c, then there are more nodes in the graph, and there will be, at all times, an infinite component, which will look more like this. So there is a component going from top to bottom, left to right, spanning the whole region. So back in the summer, we studied with Yuval Perez, Alistair Sinclair, Perla Susi, and the last S is me. We studied this large deviation results for some stopping times, so probability that it's stopping times larger than t, and we studied this for this stopping time being the detection time, which the first time some node of the graph is able to detect the presence of a target that can be either fixed or moving. And the percolation time, which is the first time at which a given node first belongs to the infinite component. Right? And we also analyzed the coverage time and the broadcast time. And related to broadcast, now I'm going to show you, I think, the only concrete open problem of this talk. It's the following. So assume the following situation. You want note that nodes are moving in continuous time, but they are able to send the message to their neighbors, immediate neighbors, in discrete time. So a node has a message at time 0, then at time 1 it looks at its current neighbors and send the message to all of them, and do this at each discrete time step. Right? So this process, we know it was analyzed by, in similar model by Harry Kast and Vlada Sidoravicius in this century. Not sure if that's 2004 or 3. And they show that the size of the informed set grows linearly with time. Okay? Now the question is, okay, but what if the nodes have an alarm, say a Poissonian alarm? Okay? When they receive the message for the first time, they set the alarm, and they, at each discrete time, they spread the message to their current neighbors, but after the alarm rings, they stop and never participate in the dissemination again. It means this can be a model for the scenario where nodes are like moving sensors in a network and they want to save power, so after some step they just stop sending message. Or the case where spread of infection, that's the sad case, the node just dies. And the question is there a value for mu sufficiently large for which this process survives or not?
Yes. Small rate.
Oh, you're talking about rates, yes.
So this discrete time business, is that important?
No, it's not important. It's just to simplify. Because then I would have 2 Poisson clocks. My explanation would be weird.
But you could just broadcast whoever you touch instantaneously if you want.
Oh. No. Because then you would touch the infinite component, and that's. But there would be a difference between the supercritical and the subcritical case. That's a good point. But that's my only concrete problem for the talk. And then let me just talk about a technical thing and some develops on this technical thing and some open problems about this technical thing. So the technical thing, what's this? Okay. In our analysis, it was very handy, a coupling argument that first appeared in a joint work of myself and Alisa Sinclair, and then in the work we did here in the summer. And just quick remind is, these nodes are moving around, and suppose you look at a finite box, and you tessellate it like this. And it turns out at some time that all the cells have sufficiently many nodes. For example, here in the picture, all the cells have 2 nodes. But pick a number. Cells have that many nodes. And we call this the event that the cells are dense. And then we can show that we can add to the picture an independent Poisson-point process with smaller intensity. Say they have like different colors. And then they can couple the evolution of these nodes and the independent Poisson-point process so that after some steps that depend on the size of the cell, they couple in a way that...
You choose a grid at the beginning, a certain size, or what?
Yes, you can fix the size of the grid.
No, but the number of cells, n by n, or what have you got here?
Oh,
you can't have it infinite.
No, you cannot have infinite.
Exactly.
Yes,
so what's your choice here?
It can be anything very large in k. It cannot be exponentially large in k. It can be polynomially large in k.
Yeah, but I was just asking what you were choosing.
Well, it depends on the application. Usually the size depends on the time you are observing the process completely. So that arguing about the finite case is the same as arguing about the infinite case. That's essentially, for example, if you run the process for t steps, you can...
Asking for your choice, your particular choice.
Because I apply this in different problems. So it's up to your flavor. But for example, just to give a concrete example, we use time t squared, for example, in our analysis for the percolation time. Size t squared. To give a concrete example. So then you can do this coupling so that after you skip the steps, if you look at the subset of this region, smaller size of the box, then the nodes will contain this independent Poisson-point process. Right? So this allows you to forget the past. Right? You recover independence by skipping some steps. Okay, that was very handy. And there are 2 simple extensions. The first one is the simplest. It's an ongoing work with Alisa Sinclair. And we actually need this to happen, but only allowing nodes to move in a ball around it. It cannot escape a ball around it. And the reason why we need this, well, the same thing works. It's not as trivial as you think because the coupling has some details to be sorted out. But the reason we need this is that we need to analyze sometimes this process in different areas of the space at the same time, like in multi-scale arguments. Right? And when you do this, you want this coupling to be applied in different areas and not interfere with one another. You should be able to apply them independently. So that's why we force the nodes not to move too much so they can't go to a region and come back. Right? They have to stay around their position. So we're able to get the same results by assuming the nodes cannot move too much. And the second is in a joint work with the Benjamini. It's also an ongoing work. And we're able to give the other side of the coin, which says that we're able to couple the nodes so that the nodes are contained in an independent Poisson-point process, assuming that all the cells are not too dense. That's one thing. That's almost the same analysis as before. But the interesting thing is that we are able to work, in our case, with unbounded regions. You can take the whole Euclidean space. I'll explain what that means. You take the whole Euclidean space, the whole R2, you tessellate it. If you assume that all cells are dense, then you are able to apply this coupling so that not everywhere, but almost everywhere in the region, the couple will succeed. Well, almost everywhere means in a percolating cluster of a tessellation. Right? You can just show that there will be a percolating cluster like this hatched area here, at which the coupling succeeds. In the other areas, the coupling may not succeed, but these are very bounded, and in our case, this was sufficient. And this turns us to two speculative questions. So the first one is with the result of the tie, we actually show that in this percolating cluster, the nodes are sandwiched between two Poisson point processes. Right? They contain a Poisson point process, and they are contained in another one. So they show that in some sense, they converge to a Poisson point process. And the question is whether we can do similar analysis for other point processes or not. Whether if you take a point process, assume a translation invariant, and now let them move as a Brownian motion. Now, of course, you have dependence all over. Not all cells will be dense, but have to deal with that. But can you somehow argue that the approach, the conversion, this sense of the sandwiching argument, an independent Poisson point process? That's a very speculative question. And the other one is whether you can apply the coupling argument for the same way I was telling before, but for other types of motions. That's always when I give this talk, someone that works in network asks me, and what about other types of motions? Because no one moves as a Brownian motion. No one can do a motion that's nowhere derivable. Okay. And that's the point. So can you do a coupling with other types of motion or not? And the main thing here is you'd need like a coupling time for each time of motion. And if you can make something rigorous out of that, it would be important for people that study this in practice. So let me just sum up and just realize that talking about sandwiching before lunch is not a good thing. So let me finish the talk quickly. So I just showed you my work on mobile geometry graph very quickly and randomized broadcast. I didn't have time to show you my work on mixing time of Markov chains, and I also have ongoing works on that and the performance of sampling algorithms, especially importance sampling. But I would be very happy to talk with you offline about any of these things and other things, and life in Seattle, the weather that's nice today, and everything. Thank you for your attention.
Any questions?
I was hoping to hear about the sausages as well.
So, Alexander's here until tomorrow?
I'm until tomorrow.
Tomorrow, so we'll find some. Okay.
We have some gaps in the schedule.
Yes, there are some gaps.
Just, I guess, silly question, but if you, instead of Brownian motion, you asked about other motions. If you sort of discretize it, can you still couple? I mean, if you wait a random time, make a random step on the right side, I don't know, something.
You mean for Brownian motion or for?
No, so
For
you want to avoid the totally.
If perhaps.
Suppose you just do a simple random walk there.
Yeah, that works.
That works, right?
Yeah. Essentially, anything that. Not anything, I won't say that. But random walk, yes, for sure. I mean, everything that looks like normal distribution that time will work. Because that's the only thing we use. Thank you.